All right, welcome back. The next talk is by Klim, and he's going to talk about binary code with resilience beyond one port via interaction.
Okay, thank you. It's really nice to be here. And so first of all, this work is with my good friends, Raj, Gilad, and Jing. So what I want to tell you, like it's some result that like I was really surprised. So like when we started to work about this, we believed that it's impossible. But I have to say, like I will tell you like probably bigger story about interactive coding. And I have to say, like what I like about working in this field of interactive coding is that you almost always like, okay, you have some, you start thinking about some problem, you have some conjecture, it's almost a probability one being false. Like when you start working on this, you discover that the true answer is like something completely different. And it's like, I really like this field, so, and I really suggest you, like, if you haven't saw this field yet, like to read a little bit more about it. So I'll try to give you some overview. So first of all, let's start. So today I want to talk about like probably most basic question in error-corrected code. You have Alice and Bob. There is some noise in the middle, and Alice wants to send message to Bob. Okay, so this is probably most basic question in error-corrected codes. So what Alice has, she has k bits of message. She calls it to sublogger message at bits, and then sends it to Bob. And like I believe that everyone, so in this audience, I can assume that everyone saw Plotkin bound, and Plotkin bound says that the maximal distance of error-corrected codes you can get is 1/2. So this way I wrote this has some asterisks. So I'm going to get to this asterisk, and asterisk means that the length of the code should go to infinity. Okay, it can go arbitrarily slow, but it should go to infinity. And we are not talking, and I want to mention here so that we'll be on the same page, because like it's something that usually very confuses people. We are not talking here, we are even not talking here about rate. So rate can be arbitrarily slow, like it can be double exponential, whatever. It's still 1/2. So, and most of the talk, I'm not going to talk about rates. I'll only assume, sometimes I'll assume that it's just positive, but rate will be not the major of my major focus of my talk. Okay. And now the question I want to ask is the following: what happens if you have the same task? Alice wants to send message to Bob, but now we allow interaction. This means that not only Alice can talk, but also Bob can talk. Okay, I will not going to keep you hard. And like what I'm going to show today is that what we can have a constant rate binary interactive coding scheme for message transfer. Message transfer means that Alice can send actually message to Bob, and such that this coding scheme is resilient to greater amount of noise than 1/4. So we're actually breaking Plotkin bound. So like, you know, when you're thinking about Plotkin bound is false, like, wow, like it's some, like, you know, it's like these columns will like go down here. Like it's something that you feel so basic for error-corrected codes when you learn about it. So like it was amazing. So, and this work was started like, okay, let's show Plotkin bound for interactive communication. It turns out to be false.
I have a question. Yeah. What do you think is the truth here? Like, by how much can you break Plotkin?
I don't know.
But
no, I just don't know. Like,
it's with one probability false. If you have a conjecture, it's with one probability false.
Yeah, no, but you know, when I give you conjecture, like I really believe it is. So.
I have a question. How does this relate to the 1/3 we saw yesterday in talk about Rachel's talk with feedback?
Wait, Rachel talked with feedback. She gave 1/3.
That was no noisy. The feedback was not noisy.
The feedback. Okay, so the feedback was so where A, the feedback was not noisy, and B, it doesn't count towards the communication. Okay, so the B is maybe less important, but the important part, it was like not noiseless feedback. So here, like here, okay, so the coding scheme here will be pretty easy. Like it's Alice sends message, Bob replies, and then Alice. So it will be 3 round, and like adversary can like do whatever he wants. If he wants, he can corrupt the feedback. If he wants, he can corrupt any messages. So like it will be like okay. So at the end it will be not that easy, but like it's a 3 round. So there is no like hidden things here. And if you allow noisy feedback, then it's you can get 1/3. I'll get actually to this.
So, is it obvious upper bound? Is there like an obvious upper bound that you?
Obvious upper bound of this, I think to 7, but Megal told me that 2/7. It's not obvious, but it's not very hard to show. But Megal said that they had a better, right? You have something better.
Yeah, I think you can show an upper bound of like 13/47 or something. Yeah. Okay. No, it's a little bit more I don't need to show, but I think even that is unlikely to be tight. So I don't really know what the answer is.
So yeah, we just don't know. Like it's like it's amazing open question. So it's probably a few years until we'll solve it. Like no, I mean all we. Like, but I believe it's solvable at some point.
The question is open even if you don't care about rate, right? Number of rounds.
Yeah. So it's not a question about rate. But you want the number of possible messages to go to infinity. So you don't want that you want to send 1 bit where it's okay. So now I want what I want to do. I want to give you some kind of overview of interactive coding. A, because I love it. B, because like in order to explain this result, I will need you to understand how. Okay. And, first of all, I want to say like what type of questions we can ask. And in this talk, I'm going to talk about like three questions. And one question is like message transfer. Okay, so I have a message. I want to transfer it to you. You don't want. You are not interested to delivering any information to it. Second task is I'm going to talk is message exchange. We both wanted. So you have a message. You want to send it to me. I have a message. I want to send it to you. How we exchange our messages. And the third task, like which is like coding for interactive communication, which is like the main task we're usually interested, but I'll probably be more focused about this task because they're simpler and more basic, is interactive communication. So Alice and Bob has input. Their goal is to compute some function f of xy, and they do it in several rounds using some interactive communication. And in general, like this task can be reduced to message exchange task because like if Alice will just send her input to Bob, Bob can just by himself calculate what is f of xy. So, but usually when we talk about the third task, we also talk about rate because this kind of protocol sending your whole input to another party will usually incur exponential blow up in your rate. Okay, so these 3 tasks we are going to talk. So now let's talk about what's known about message exchange. So very naive way, let's say Alice takes her input, encodes it's an error correcting code, sends it to Bob. Bob has his input, encodes error correcting code, sends it to Alice. What's best? So this thing will give you a resilience of 1/8. Why it gives you a resilience of 1/8? Because each error correcting code is resilient to 1/4. And if adversary like concentrates on one party who speaks less, then he can corrupt this party. I will mention here, I said concentrates on one party who speaks less. So here I'm assuming so far non-adaptive. I will talk about this a little bit later. But this is like naive generalization that gives you 1/8. And in general, Braverman and Rao generalized, like extended this result of 1/8. So for any interactive task, so if you want to compute, this is like a completely non-trivial result. So if you want to compute if you have a protocol that, like say, in T rounds computes any function, then you can have a resilient protocol which is resilient to 1/8 minus epsilon fraction of errors. The computes like in subconstant like 1 over time 1 over epsilon squared times T routes this function. Okay. So like the basic building scheme for our results to get something better than one quarter was that we can improve this 1/8. Okay, and this actually was like super surprised because like when we started to work on this 1/8, you also believed that it's tight, and it's actually I not sure if it's definitely Braver and Rao definitely asked this question. I think it doesn't conjecture that 1/8 is tight because they were more cautious than other people. But yeah, right. What is that? Anyway. So in my opinion, like it was very surprising. Like, okay, so like knowledge that we know so far, it's not very surprising because like we know what's like, you know, after you work enough time on the field, you know what's important places to what's important things that you can do. But like it was like actually very surprising, and we could. And I want to mention that in fact like Rachel and Megan. Sorry, it's like very. Okay. Rachel and Megan, like they actually like get an optimal bound for this problem. So if you want a message, if you want to have like, if you two parties want to exchange their messages, they can have an a resilience of 1/6, and they have a later work. If it's not updated, they have a later work that it works not only for message exchange but also for simulating any interactive protocol. So, questions so far? Okay. I want to talk a little bit more about message exchange, what we know about over a large alphabet, because it's okay. So so here when I'm talking about large alphabet, it's like some alphabet which is constant but can depend on epsilon. This is what I mean large, and if you want if two parties want just to exchange their messages, then 1/4 is tight. Why it's like the trivial lower bound is just like take your message encode with error correction code, send to another party also takes his message and send by error correction code. And the lower bound is the reason for lower bound is that adversary can concentrate on one party who speaks less, corrupt 1/2 of his communication, and since adversary like speaks more than this party, like there is no way we can distinguish between two of them. So like therefore he will be able to corrupt our communication. But there was like a really nice paper by Grafari, Haupler, and Sudad, and they asked a really nice question. Okay, so what here assumed the lower bound? He assumes that adversary can somehow figure out who is speaking less. Okay, but what happens if you adapt? What does it mean we will adapt? It means that our protocol, we are not fixing who is going to speak at every round in advance. But based on what we see in our communication, we can decide who is going to speak. Okay, and it's surprising that like so once need to define the model. What happens if both parties are speaking? What happens if both parties are listening? So like it's usually what the definition is like the worst things are happening. So that like you know, like adversary can decide whatever. Okay, and they showed that 2/7 is actually is achievable, and in very strong sense conjecture that it's tight. So it turns out that so like this oversaw conjecture, like it turns out that it's false, and it was like really surprising. So what we showed, that the real result is like some 5/16. But what I want to say, okay, so I want to say like why I'm so excited about this result, because like somehow like you think like, okay, so there is like a task of like with two people wants to exchange their messages. So it's a very symmetric task, right? There is no like Alice is not better than Bob or Bob not better than Alice, right? So they are very symmetric. They are trying to do the same thing. So you'd expect that your protocol will be also symmetric. And it turns out that if your protocol is actually symmetric in some sense, then 2/7 is actually the right answer. And like somehow, like we actually, in order to achieve this answer, we actually had to build a protocol which is non-symmetric. So like one party like needs to speak more than another, and we can show that like it's a tight result. So we know that it's what we have to do. And moreover, it's interesting that it must be there a situation where like in some scenarios like that both parties are listening or both parties are speaking. So it's you know, there is like this rule of thumb that if you're always if you're never late to airplane, then it means you're coming too early. So this is like the same thing. It's like if your model allows you to do some stuff you're never doing, it's probably you're not probably tight. So
Is it like good intuition to have for that? Is in the example that you have the adversary kind of focused on one party, so that's why you need to be asymmetric to kind of overcome that?
No, actually, the reason is not like adversary can focus on one party, but if he's like focusing too much on one party, then you'll at some point of time like you'll figure out that he's focusing on this party and you'll let him to talk more. The reason actually is the feedback. So like one party is like talking, another party is giving the feedback. So this is the reason why it has to be asymmetric. So because like if two parties are talking like kind of together or in some symmetric way, you will not be able to implement this ideal feedback. I want to like okay, so I want to say that like although like we are working for some while in on these questions, like very basic questions like still open. So this question is like only when we want to do message transfer. What is maximum noise resilience for interactive coding over adaptive channel? So, and here, like here again, we want a constant rate. So because like, otherwise it will be trivial. And we actually don't know this question. I believe it's solvable. I believe it's just a little bit hard, but it's solvable. But, yeah.
Was 2/7 achievable for general interactive coding over adaptive?
Yes.
That's correct. So it's somewhere between like 2/7 and I guess 1/2. Is that correct?
It's more. It's more than 2/7. It's definitely know that it's more than 2/7, and it's less than this.
Okay. So
Because like this lower bounds apply for general interactive coding, but and I think we know that it's strictly less than this. So like yeah, so when we get some numbers like 5, actually 5/16 is a nice number. It's the radius of least decoding with size 3. So you know, like you get way too many numbers, so you get familiar. Anyway. Anyway. Now, like we'll ask the question. So this is our main theory. What happens if only Alice wants to send the message and we allow communication? And it turns out that we can break 1 quarter. What's again?
Is this adaptive or non-adaptive?
This theorem is 3 rounds non-adaptive. So like, okay, so it's how I see it like a proof of concept. that that you can actually break it, but yeah, so like probably you can have like more more complicated schemes. Okay. What I want to say, it's like it's also open problem and so on. But what I want to say that we will have here to use like somehow like machinery. We'll need to use somehow like very asymmetric codes, okay, and somehow the distances that are between like different code words will depend on the messages that you are encoding. So sometimes you want that the distances will be larger, sometimes it will be smaller. So it requires some kind of very asymmetric recurrency codes. Okay. I want to also like mention wait. A paper by Yael Gupta and Rachel. That they actually can get like the same question, but what happens when we have only erasures? And in fact, you can get here to 3/5, and like also getting optimal error resilience is like it's a good question. They conjecture it's 2/3, and I believe it's conjecture. So like here is another conjecture. You can try to make it false. Like it's very fast because like you really believe it's conjecture until it proved false, and when you say how you can believe it's conjecture. Anyway, now let's okay. So here so far is kind of overview. So if you have any questions, I will go like move to more technical stuff. Okay, first of all, I wanted to say. The error resilience barrier. Why? Like, so I want to now to talk about this result. Okay, so because in order to, I'm not sure if we'll get to 1/4 result. Like, but if someone will want, he can catch me. And actually, this slide goes to all the technical details of 1/4, and just will take me. Usually, it takes me just a little bit more than 45 minutes. Okay. So now, if you want, now I'm going to ask the following question. You have Alice and Bob. They want to exchange their messages, okay? And I want to ask, like, why it's very hard to get 1/8. There are like 3 reasons why you get 1/8. One reason is that we ask this question over binary alphabet. Second reason is that we want to have unique decoding, and the third reason is that it's a 2-way task, so that we want both Alice to get message and Bob to get message. Okay, so there are like 3 reasons, and somehow like each of these reasons like give you factor of 1/2 to your solution. So this is the reason why you get one. Like trivial solutions gives you 1/8. Okay, because like we know that like for example binary alphabet best distance is 1/2, while like regular alphabet best distances can go all the way up to 1. In unique decoding versus least decoding, you also lose factor of 1/2, and in 2-way task you also lose 1/2. Okay, so when I gave like this result that that you can get 5/39 was before I got the result about unique decoding. So we had like even better explanation that any 2 of these are also like gives you 1/4. So like indeed, if you want unique decoding over large alphabet, then you can 1/4 is tight. Also, if you have a binary alphabet and like least decoding, also you can show it 1/4 is tight in paper with Mark. And we had also this. I deleted it. We had also this thing. Which is like now I deleted it. I had to delete it because it's like back then I really believed that this is true, right? That if you have binary alphabet and unique decoding, then 1/4 is the best you can get. But now I actually had to delete it. So this is like why how strongly I believed that it's true. So, but anyway, so in order to get something better than 1/8, we need to combine all these 3 things. And like one main thing like that comes to our help is what's called feedback. And feedback, like it's a very somehow like it's a very strong thing in interactive communication. Like in fact, like when I want to talk with you, I can not only send what I want to say to you, I also can reflect what I heard from you. So it's actually like, I feel like it's a very instructive message, like in real life, like not only try to say what you heard from other person, but also reflect what you heard from him. It really helps to communication. It's also my real belief that it also helps in real life communication. It's affects on rate, but it makes sometimes communication possible where otherwise it wouldn't be possible. No, it's like you can really like write from this research like a philosophy book, and it's very consistent with like philosophical messages that you want to say. How till what time do you have? to this result. Okay, so and there is like really nice paper by Berlekamp. I think it was his thesis. He actually like get that your channel feedback can achieve 1/3 of error rate, and he gives like I think it's he gave like optimal rate versus distance bound there. So it's a very nice paper. So and if you want just to send, so what it makes that immediately lower bound of 1/3. So if you want just to have a message transfer, so I want to transfer message to you, well, then like you cannot do anything better than just giving me feedback. So this is the only thing you can give me, and therefore like 1/3 is an optimal, like it gives you a lower bound. Yeah. So, and it also gives you like 1/6 lower bound for message exchange. And here we are talking about if it's non-adaptive. Okay, so if it's adaptive, it's another story. Okay, now I want to show you protocol that for message exchange, and it's a relatively simple protocol. It has like a minimal number of rounds, which makes sense, which is 3, because less than 3 it's not interesting. And I will do the following. The length of my protocol, if you'll count, will be 39n. Okay, so it's 39n, and the number of errors is 5. Okay, like it's scaled with some number. Okay, it's just less than 5. And here it's what is we are going to do. So the protocol is the following. What Alice is going to do? Alice is going to send her message with some least decodable code. And the length of this first chunk is 16. And it's least decodable code with list of size 3. And like it's a nice coincidence that error resilience of least decodable codes with list of size 3 is 5/16. It's maybe not everyone made this calculation, but actually I'm now giving it as a homework in my course. But anyway, second, here is like because we are like kind of a little bit ignoring the questions of rate. What Bob is going to do? He's sending message of length 20. So he's actually resilient. So the maximum amount of errors that adversary can put here is at most 1/4. So he can actually transfer his message. What he can do, he is sending his message together with a list.
So that's like the feedback.
Yeah, this list is kind of feedback. Okay. And now just the third part of a protocol. It's like it's a small part. I'll just send which one of these elements in the list is the correct one. And here, like, okay, let's look on this protocol. And I want to ask, like, why cannot you just the same way you still corrupting water and 1 quarter, so you can corrupt 1 quarter for here, 1 quarter for here. What's so you're corrupting 1 quarter from of communication from Alice. So why it's still communication is possible? And the reason is somehow that last part, okay. So Plotkin bound is not tight when your message is of size 3. So, and this is kind of important, right? So what you can have this code, and it's very easy to see that its distance is 2/3, so it's resilient to 1/3 of errors.
The last code is just repetition.
What?
The last code, the smallest EC that sends 3 bits, or whatever.
No, it's
This one also.
it's just this code. Okay, so you can repeat it, like you can scale it, you can repeat it. It's just 0, 0, 0, and then 1 and 1 coordinate. So it's a distance, and 2 coordinates and 1 and 2. It's nothing like very fancy, right? It's very easy. And then what will happen now? Okay. So I will go over several I will not going to give a full proof that it works. I'll just my rule of thumb is that you need to go over all extremal cases and then check that they works, and then actually write a proof in order to check that what you get is all extremal cases. But I'll just go here over all extremal cases, so show that it works, and then regular arguments will show in the middle. So if adversary just concentrates on, so first of all, adversary just cannot corrupt the message from Bob. Okay. One thing that adversary can do, he can try to concentrate here, right? And trying to corrupt this, but because we know that least decoding radius is 5/16, so this Bob will actually for sure will get his list, and then after he'll send back his list, so Bob will actually receive his index. But the problem here is that adversary actually can corrupt completely this part. And in fact, adversary, what he could do, he could spend two messages, 2 corruptions here, 2 n corruptions here, such that instead of thinking that the correct index is first, I'll think the correct index is second. So it looks like it will completely ruin this part. But I think if he spends 2 corruptions here, he left only the 3 corruptions here. And here we will assume that our code is a good code. It means that distance between any 2 codes is a distance 8. So if you're spending at most 3 corruptions here, okay, then it means that we know for sure that the answer that we get is correct answer, because the second answer will be a distance at least 5 add from because it's the distance of code is 8. If you're spending 3 corruptions, like a regular triangle equality, show that all other answers will have at least 5 corruptions. So we know that they're impossible. And the last thing that thing that adversary could do, he could spend 1 corruption here, and then we have no clue what index is, but then we know that 1 corruption here is spent. So we know that we need to output the best answer from here and just ignore it. So all these 3 cases works, and you can interpolate between them. Great. Powerful, like powerful binary codes. Anyway, so what I want is here is we need least decoding interactions and binary codes. Now I will try to say a little bit. So I will try to say a little bit of obstacles why it's hard for getting from message how from message exchange to message transfer, and the reason is if we try to implement the same thing, right? So like just regular limitations, we will see that because it's enough to corrupt one. If we are able to corrupt 1/3 of communication from Alice to Bob, we are dead, right? So therefore, the amount of communication that Bob can send will be really, really tiny. Like we can bound somehow. But then what will happen? What will happen is that in this case we can completely corrupt communication from Bob, and like we no more can like get like this kind of feedback, which is we can trust on it or we can build on it. And then we tried like to do different tasks, but there is like we had like this theorem that even like this task when Alice has his input and Bob list decodes Alice's input to the list of size 2 x and y, and even more, let's say Alice almost knows what is Bob's input. Like Alice list decodes Bob's input also to the list of size 2. So even then, like we wanted like to somehow to use some small codes, but even then we know that the communication complexity of this task is at least omega of log n. So what happened? Okay, anyway. I'll continue without. It's fine. Okay, it's fine. Okay, so and like this, like when we had this, like this made us like completely sure that 1/4 is the best what you can get. So, and the problem, like even like we cannot make sure that list decoding is possible in the second stage, and what we need, we actually need what's called non-equally spaced codes. And like in regular recursive codes, what we interested like is like, okay, what's the like minimal distance between any two codes? But here we want somehow like in some cases we wanted that if some of our messages that we send, then the distance will be very large, and in some cases when the distance will maybe a little bit smaller, because we know that there was like some errors in our case, and so we built like somehow like a very it should be like a very new muted codes built for this. It's actually not very hard to get what exactly we want and how to get it, but it will require me 44 more minutes. So I think I'll stop here. So like, okay, so I want to say that Plotkin bounds holds even for like average distance. So we need somehow, it's a very like suited thing. But I'll stop here. I'll let time for questions. That if someone wants, like, I'll be really happy like to give all the details. So
say a bit about which pairs of messages are more likely to make errors? I don't know.
No, I can, but you'll have to stay for like another half hour. Like it's actually like this idea was also mentioned in your works, right? Where, but yeah, but it will take.
More questions? Okay, let's thank you.
Maybe you said this and I've forgotten, but over large alphabets for message transfer with noisy feedback.
Okay, so so I didn't say that. It's a great question. Over large alphabet, you cannot get so over large alphabet, when I'm saying large, I mean like a constant depending on epsilon. You cannot get anything better than 1/2. You can probably get something from feedback, right? So but like for example, if your alphabet is like 3, I don't know the answer. Okay, so it's but when your message becomes bigger and bigger, just feedback doesn't help you in terms of noise resilience. So in this case, it's
Yeah, you won't be 1/2, I guess. Is the conclusion.
yeah, it's about what you can break. So like we probably like if adversary speaks more than you
Oh, true. Yeah, you can use the same.
yeah, so it's,
Yeah.
All right. Thank you.